Hello everyone, my name is Max, and today I'll be discussing the second derivative and the information that we can gain from it. Now, a little bit of notation to start. We can denote a function as f of x, the first derivative of the function as f prime of x, or df dx, and the second derivative of the function as f double prime of x, or d squared f dx squared. In this video, I'll be using the prime notation to denote the derivatives of a function. Now, what do these derivatives describe? Well, the first derivative describes the slope of a function, and the second derivative describes the change in slope of the function. If the second derivative is less than 0 at a point or over an interval, we say that the function is concave down. And if the second derivative is greater than 0, we say that it's concave up. Now, this concavity language just refers to the change in slope of the function. And this information can be useful. For example, we know that if we set the first derivative of a function equal to 0, we can solve for local maxima and local minima of the function. But we don't always know which it is. If we examine the second derivative at those points, if it's less than 0 or concave down, we know that it's a local maximum. If it's greater than 0 or concave up, it's a local minimum. Now, an example, let's say f of x, our function, is equal to 2x to the 5th plus 3x squared, and this graph to the right is a graph of that function. The first derivative of the function will be 10x to the 4th plus 6x, and the second derivative would be 40x cubed plus 6. Now, we could ask ourselves questions such as this. At the point negative 1, 1, is the function concave up or concave down? And we know that we can answer that with the second derivative. If we plug in x equals negative 1 to the second derivative and solve, we'll find we get negative 34, which is less than 0. And if we go back a couple slides to this reference, we know that if the second derivative is less than 0, it must be concave down and is a local maximum. And that's what we see if we look at the graph. The black dot is that point negative 1, 1, and the function is concave down at that point. Now, the other information that can be gained by the second derivative are inflection points, and these describe when the function changes from being concave down to concave up, or vice versa, from being concave up to being concave down. And we solve for them by setting the second derivative equal to 0 and then solving for x. If we stick with the example that we had on the previous slide, we know that the second derivative is 40x cubed plus 6. If we set that equal to 0 and solve, we get x is approximately equal to negative 0.53. Now, we do have to be careful when we are plugging in points to this second derivative to determine if it's concave up or concave down, or trying to gain other information. And the reason is because when we take the derivative or successive derivatives of a function, sometimes the domain of that function will change. And so we need to be careful that when we're plugging in some values trying to get information about the function, that the function is actually defined at that point. So here's an example. We have a function is equal to the natural log of x squared minus 3. Now, we know that the natural log, we can't take the natural log of 0 or a negative number. So if we say x squared minus 3 must be greater than 0 and solve, we get that x must be greater than square root of 3, and x must be less than, or alternatively, x must be less than the square root of 3. So we get a domain which does not include that region between negative square root of 3 and square root of 3. However, if we examine the first and second derivative of our function, we can see that those do not contain the natural log. They do have a denominator, and we don't want to be dividing by 0. So if we examine the cases when the denominator is equal to 0, those are at the points x is equal to square root of 3 and x is equal to negative square root of 3. So our domain for our first and second derivative does not include those points. However, that is a less restrictive domain than the domain of our original function. And we can see visually our original function is in blue, the first derivative is in green, and the second derivative is in purple. And we can see the kind of difference in domain and the larger domain restriction of the original function. And so when we're playing with the second derivative and plugging in points, we just need to make sure that the points we are plugging in are defined in the original function. If not, the information that we're gaining is incorrect. And so that is a little bit about the second derivative of a function and the information that can be gained from it. And if you're looking for more information, this is a great site from Wolfram Alpha. Thanks.